Let me now describe to you the Octave script file that we will use to obtain the friction factor using the Colebrook-White formula. So here on the screen I have ASCII script file colebrook.m. It's an M file to be run in Octave. You could, with probably slight modifications for compatibility, also run on MATLAB. I haven't tried running it on MATLAB. I will provide this as a resource. You can experiment with it and then try to see if you can run in MATLAB and Octave. So I am writing a function file, function output f, which is the friction factor. I am calling the function name as Colebrook. I have used the same file name colebrook.m, and I am providing two inputs, R, Reynolds number, comma ed. Ed is the other input, which is the roughness ratio. Ed is actually E by D, epsilon by D, that we have used in the Colebrook equation. Okay, after the comments, then let us come here. There is a number of input arguments check. Then now let us do the main program. So the main program is actually distributed into an if loop. So there is one if condition where the flow is checked. So the Reynolds number should be positive and R less than 2000. So between 0 and 2000 we have seen that the flow is laminar, and the equation used is F is equal to 64 by Reynolds number. So this will give the friction factor if the flow is laminar. Else, if the value of the Reynolds number is greater than 4000 and we say that the flow is turbulent, so we will use the Colebrook equation. So I am using these identities, A, which is equal to epsilon by D by 3.7. This is what we used in our iterative relationship. B is 2.51 by Reynolds number. Now xk, the initial value of the xk, I am going to set it as 1 by square root of 0.1 as discussed earlier. And I will use a variable delta and set it as xk. Later within the loop I am going to use delta as the difference between the previous, present and the previous. Now let us enter a while loop. While this delta, the difference between the present estimate and the previous estimate, is greater than 0.0001, it's a small value, because the to find the roots, the iterative equation should converge, and as it converges and goes to a value less than 0.0001, let it come out of the loop. So while delta is greater than so much, perform all these operations. So xkk is what I am using for xk plus 1, which is equal to, this is the Colebrook equation, iterative equation which we derived. Then delta is xk plus 1 minus xk, is basically delta x, and I am setting xk to the new value, new estimate, whatever that xk plus 1 estimate is, so that the loop can continue. And once delta has come lesser than this value, then comes out of the end while, and the friction factor is 1 by xk square. So this is the friction factor. So for turbulent flow we apply this Colebrook iterative relationship. Else meaning what happens if the Reynolds number is between 2000 and 4000. So it will come into the else condition. So here it is actually a transition between laminar to turbulent, turbulent to laminar. So there is no well-defined relationship. What I have done is F laminar is 64 by R, and F turbulent is, I have repeated this equation set here, evaluated at whatever the value of Reynolds number that we have passed into the function, and I am taking the max value. Max value of friction factor will give you the worst case HF, worst case friction loss component, so that we are safe when we are doing design. So it will be a conservative value. So I am computing the F using the laminar equation, computing the F using the turbulent equation using Colebrook's formula, and then taking the maximum value among these two to take as the conservative value of the friction factor for the transition region. So this is the function that we will be using for finding the friction factor. Now for example, let us go into Octave and then call this Colebrook function. So how will you call it? So let us say I want to know the friction factor, Colebrook, and let me give the Reynolds number. You see, we have to give the Reynolds number and E by D. So let us say Reynolds number of 5000, and let us say E by D, roughness ratio of 0.001. So this will give you a friction factor of 0.038495. Same thing if you had used PVC for the pipes. If you had used PVC for the pipes, the roughness ratio would be 0, and for the same Reynolds number of 5000, you will get a friction factor 0.037, slightly lower. So the Colebrook function can be used now to find the friction factor for any given value of the Reynolds number. We can also use this Colebrook function to make our own Moody chart. Though we may not use the Moody chart for design, we will directly use this Colebrook function to give the friction factor for a given Reynolds number and epsilon by D roughness ratio. It will give some insight and understanding to develop our own Moody chart, not only for exercise purpose, but also to cross-check with the Moody charts which are there in the literature and to validate that our Colebrook function is correct. So I have here prepared a very small script file in Octave, file that calculates and plots the Moody chart for friction factor estimation based on the Colebrook-White formula. So what I will do, the x-axis I am defining as the Reynolds number. I am sweeping the x-axis with Reynolds number value from 10 to the power of 3 to 10 to the power of 7. I am using log space, logarithmically spaced points from 10 to the power of 3 to 10 to the power of 7. That is the Reynolds number. It's a vector now. And the roughness factor, I have just given few select points that in the literature there were certain roughness ratios that were used. So I have used the same roughness ratio value so that I can compare the graphs I get from this Moody chart with the Moody chart of the literature. And then I use one for loop for incrementing the roughness ratio, another for loop for incrementing the Reynolds number vector. And after that, within the innermost loop, you call the Colebrook with the value of Reynolds number updated every time for a given roughness ratio, and then you will get an output where F is a vector matrix. You will have one row for every value of roughness ratio, and then plot. So plotting is log. Normally you would have seen the Moody chart which I discussed earlier. Both the x-axis and the y-axis are logarithmically scaled. So it's a log graph of Reynolds number on the x-axis versus the friction factor on the y-axis, you will get a family of curves based on the roughness ratio as a variable, as a parameter. So this is the script that you will use for obtaining the Moody chart. We can execute it and then just see. So let me type in Moody chart. So you see that the Moody chart is something like this, and this is the Moody chart that I also showed to you and discussed with you. This y-axis is the friction factor, x-axis is the Reynolds number starting from 1000 to 10 to the power of 7. Reynolds friction factor is from 0.01 to 0.1. Now you have this family of curves here. The parameter is the roughness ratio. This is at 0.0001. This is 0.04, like that. I went to Google and then went to this particular site here to look at the Moody chart. You see that there is a Moody chart given here, and for similar values of roughness ratios which I have chosen in the Octave script. You can actually compare it with the Moody chart that we have generated using the Octave script. Both are similar. In fact, the values are also exactly the same for the various roughness index. So this actually verifies. You see, this is the laminar portion, this is the laminar portion, a single line going in there, and the turbulent portion starts from here. This is the turbulent portion, and if you cross check for each of the roughness index, the values will turn out to be the same as given in the literature. So our Colebrook's iterative algorithm is actually verified, validated by this, and you can now use that for design of your pumping system. We have talked about many parameters and many variables during our discussion on hydraulic power. Let us summarize now on calculation of the hydraulic power and hydraulic energy. So let us summarize the steps. First, specification. We need to specify the parameters. Let me come back to this later after I list down all the steps and see what are the parameters that we need to specify. Next, we calculate Q dot or dq by dt, which is Q, the discharge volume, by discharge time. These two are design spec given by the user requirement. This is in meter cube per second. Then we calculate the velocity of the fluid, knowing the discharge time and the discharge volume and the pipe dimension, especially the cross section area. Q dot by A will give you meter per second, the speed of the fluid within the pipe. Fourth, calculate the Reynolds number given by UD by nu, that is the kinematic viscosity. Fifth, calculate the roughness ratio, which is given by epsilon by the internal diameter of the pipe. Epsilon here is the height of the surface bumps in. So this express this in mm and this also in mm. Sixth, find out the friction factor. We have seen the Colebrook-White formula. We will use that function or the Moody's chart and then use Reynolds number and the roughness ratio to obtain the friction factor. 7, use the friction factor to calculate the head equivalent of the friction loss. So F into L by D into U square by 2G. This is expressed in meters. U is this value, which is the fluid velocity. G is the acceleration due to gravity. D is the internal diameter of the pipe. L is the total length of the pipe. F is the friction factor as found from point 6. Let me move this above. Like this. Yeah. Now point 8. What is the total dynamic head? H. Total dynamic head is suction head plus discharge head plus HF, the friction loss component of the head as calculated here by the Darcy-Weisbach formula. Then you calculate the hydraulic power. What is the power requirement? And this we have found out to be rho q dot gh. Rho is 1000 kg per meter cube. G is 9.81 into q dot into h expressed in watts. And energy, hydraulic energy, 1000 into 9.81 into q into h, joules. So here q dot is expressed in meter cube per second, q is expressed in meter cube, all SI units. So this is the entire step. This is the 10-point step for finding out the power and the energy for any hydraulic water pumping calculation. Now what is the specification? Let us have a look at what are the parameters that you need to specify. So first you need to specify the discharge volume. How much amount of water do you want to lift up to the overhead tank in a day or in 1 hour? These things you need to specify. Discharge volume in meter cube. Delta T is the discharge time in seconds. D is the diameter, inner diameter of the pipe in meter. A is calculated as pi by 4 d square, is the cross section area of the pipe orthogonal or normal to the direction of the flow, and this is in meter square. L is the total length of the pipe, both vertical and horizontal, because friction loss needs total length of the pipe in meters. Nu is the kinematic viscosity. We saw that for water it is 0.55 into 10 to the power of minus 6 meter square per second. Epsilon is the height of the surface bumps expressed in mm. Hs is the suction head in meters. Hd is the discharge head in meters. So all these points, all these parameters have to be specified. So you specify them and automatically every equation will follow. You can in fact put this up in a script file in Octave or MATLAB and then use this as a design file for calculating the hydraulic power and hydraulic energy requirement for a given water pumping application.